argument, it's an observation. So let's get back to malaria. And here's the mosquito Anopheles gambiae, which transmits the worst form of malaria in Africa. And here's an electron micrograph of malarial parasites, the single-celled malarial parasites eating red blood cells and bursting out from them. The nice thing about malaria, at least from one point of view, is that, I said that the E. coli work had orders of magnitude, hundreds of times more organisms than were involved in the human studies. Well, the malarial parasite has even greater numbers. Many, many more numbers of parasites exist in the world than have existed in, say, Richard Lenski's experiments. I don't know if you all remember your exponential notation, your scientific notation, but here's a little table to show that you can represent big numbers just by putting a 10 and a superscript beside it. That shows that numbers increase very rapidly. For example, 10 to the 6th is a million, 10 to the 12th is a trillion, and so on. Well, how many malarial parasites are there in the world? Well, it turns out that a person who's sick with malaria, when the malaria reproduces and grows inside him, can have on the order of 10 to the 12th a trillion cells, a trillion malarial cells in one person. And every year, hundreds of millions of people get sick with malaria. So if you work out the math, it turns out that there are on the order of 10 to the 20th malarial cells produced each year in the world. Now, to put this in perspective, 10 to the 20th, if Richard Lenski continued his experiments, he would have to continue his experiments for another billion years to get the same number of cells that occur each year in malaria. So the point is that with a huge number of cells, random mutation has that many more opportunities to come up with some lucky change, some fortunate change in an organism for which natural selection can grab onto and run with it. And it turns out that the malarial parasite has wanted to deal with some drugs that humans have invented in the past 50 years or so and find ways around them. The most effective drug against malaria for a long time, for decades, was something called chloroquine. Here's the molecular structure of it. And it kills the malarial parasite. But unfortunately, after a decade or two of using chloroquine, the malarial parasite has become resistant to it. And again, Darwinists have pointed to this as a good example of what Darwinian evolution can do. And again, they're right. But again, just like sickle cell, it points much more strongly to the limits of random mutation than to its capacities. Only about 4 or 5 years ago, the mutations that conferred resistance to chloroquine in malaria were tracked down after a lot of hard work by a number of laboratories. Here's a story from the journal Science from a few years ago, emphasizing that chloroquine is now really no longer effective because of this acquisition of resistance by malaria. And it turns out that that just like sickle cell disease involved specific changes in particular amino acids in a particular protein, hemoglobin, resistance to chloroquine does too. A protein called PFCRT, which stands for Plasmodium falciparum chloroquine resistance trait, it's just a protein that is changed, had a couple amino acids changed. And different proteins from different parts of the world turned out had anywhere from 4 to 8 changes. But 2 changes occurred in almost all of the resistance strain, here and here. And it turns out that having to change 2 or more than 1 vastly increases the difficulty of random mutation finding that combination, for the same reason that I don't know if anybody here plays Powerball. I'm sure you're all upstanding citizens don't do that. I do it all the time. As you know, if you have to match one number, it's easy. If you have to match two, it goes up exponentially. You have to match three, it goes up exponentially with the number that you have to match. The same way with changes in DNA. If you have to match more than one, matching one is really not a problem for Darwinian processes. Matching two, it starts really breathing hard. It has a tough time. For example, here's the frequency of development of resistance to two different antibiotics by the malarial parasite, P. falciparum. There is one antibiotic called atovaquone. And it turns out that in a clinical study, if you give it to 3 patients, one of those patients will have spontaneous resistance due to a malarial parasite that had a mutation in it, because you only have to change one amino acid. So resistance pops up in about every 10 to the 12th cells. But if you have to change 2, you have to get them both right. Resistance to chloroquine arises about in every billionth patient, about every 1 in 10 to the 20th cells. Now it turns out that malaria has 10 to the 20th cells occur every year, so it can overcome this without too much trouble. It's breathing hard anyway, but for larger species like humans or elephants or fish, or where the populations are much lower than 10 to the 20th, it would take many, many, many years to develop a mutation of this complexity. Now this number 10 to the 20th is actually kind of interesting if you know how to do exponents. It turns out that there have been, in the history of life on Earth, the past 4 billion years or so, there have been about 10 to the 40th cells. 10 to the 40th. You'll notice that 10 to the 40th, the exponent is about twice that. So there's good reason to think if you needed, in the history of life, a mutation that was just twice as complex as the mutation that malaria needed to overcome chloroquine, that would be beyond the capacity of life on Earth to generate by random mutation. And again, I'd like to emphasize that what I'm doing here is I'm not arguing that Darwinism cannot make complex functional systems. The data on malaria and the other examples are an observation that it does not. And in science, observation beats theory all the time. So Professor Dawkins can speculate about what he thinks Darwinian processes could do, but in nature, Darwinian processes have not been shown to do anything in particular.